My presentation is in two parts. The first part is as a paint chemist talking about paint in dry docks. So it's not hydrodynamics, it's not biology, it's very simple paint. Second part is about how roughness affects drag, and actually follows on very nicely from some of the earlier work that was presented here. This is a PhD that's currently ongoing at Newcastle University. Paint. When I was a young whippersnapper out of university and started working for International Paint, I went on a 3-week paint training course. I don't know whether other paint companies do that, but the very first day, the very first thing that was said by this elderly gentleman who gave the course is, 3/4 of a paint job is in the preparation. I've always remembered that. In fact, if you don't remember anything else from my talk, remember that. 3/4 of a good paint job when you're doing your window or doors or roof is in the preparation. And ship painting, no different. It's exactly the same. You can't make a silk purse from a sow's ear, is a quote. My good friend Daniel Kane from Propulsion Dynamics has this schematic in one of his presentations showing the sort of different roughnesses that exist on a ship. You start with the permanent roughness, which is as the ship is built. You've then got a coating. There's always a primer there, unless it's fiberglass, for anti-corrosive. You may or may not have an anti-fouling on top. You then put a new paint on, and then you get marine growth on top of that. So all of that goes together. But essentially, you have to go right back to the beginning. And what I would say is that a full blast, when you're preparing, in terms of surface preparation, a full blast always results in a good initial fuel consumption reduction. I didn't ask Nick about when he did his Indonesian vessel, whether they blasted it before they measured it, or anyone else. There are companies who make great claims for improvements when you put your new coating on compared to before the ship dry docked, but actually the credit should go to the blaster or the technical manager, superintendent who persuaded his company to spend the money to do the blasting as opposed to the new coating. So I've said whatever the coating applied, you will always get good fuel consumption figures if you blast it. And the graph here is of a hull roughness of a ship that came in at 174 microns, which is the blue line, fully blasted, and went out again at 57 microns, which is actually very good. You never normally getting under 50 microns on a ship. But this is RT50, the measure we heard about earlier. So preparation is key. Another comment I would make about hull roughness, it's measured with this instrument that you run across the surface for about 750 millimeters. And to me, it's an art, not a science. Why is that? Well, it's carried out on a clean and dry surface. But ships are not clean or dry when they're in the water. So relating this clean and dry measurement to what is going on in seawater is a leap. The second thing is, the measurement is extremely subjective. When you're going around a ship and doing a hull roughness survey, you decide your location, you look at it, and then you can select where to go. And normally, if it's your paint that you're measuring, you avoid the damaged areas, you go for the smoothest paint, you avoid the orange peel that you see, and you get a number. So you can skew the results of a hull roughness survey to get this overall average hull roughness that was talked about. And the third thing I would say is that wells and damaged areas are excluded. Now, wells will always stay the same because that's the way the ship is built. But damaged areas have a big influence. Now, going back to spot blasting versus full blasting and surface preparation, these are some figures from Propulsion Dynamics, Daniel Kane. On the left-hand side, you've got a ship. The graph is showing increased resistance from when the ship was new. This is an 8-year-old ship, so the resistance is quite high. It's in the 40s there, and it's gradually going up. Then there's a dry docking where the ship was spot blasted. Just by spot blasting, you don't need to do limited areas. The picture shows sort of what you can get. Great deal of variety. On the right-hand side, you've got a ship where the resistance is going up. It actually had an in-water clean. So that's the drop down, the first drop down. It then went to sea again, and this is only a 2-year-old ship as opposed to a 6-year-old ship. And then dry docked, fully blasted, and you can see the resistance almost goes back to what it was when the ship was new. So, the importance of surface preparation. Here's what you can actually see on a ship. These are just a couple of examples. Corrosion and cracking. If you paint over that, you will not end up with a good result. Detachment. The black is the primer, the anti-corrosive. There looks to be a serious problem here, and if you paint over that, it might look very nice when it leaves the dock, but it won't be nice for very long. This shows an area. This is after painting, and you can see the touch-up area. Well, you actually can't see it very well. It's in the middle here. There's an area of touch-up. Yeah, I must remember that. You can't see very well, can you? So, surface preparation is absolutely the key. Secondly, method of paint application. Applying paint always adds roughness to a surface. This chart here comes from a PhD that was done by Maxim Kandris at Newcastle University probably about 15 years ago. He took some towing tank panels, and this is some average hull roughness. It's the traditional way. The panel by itself had 22 microns, but when he applied a foul release coating, the number went up to 51. So just applying paint increases roughness. It's a natural event. Another point about that is that spraying gives you a smoother finish than roller or brush. Rollering, you tend to get orange peel. Brush, you get lots of brush marks. Depends on the quality of the paint, of course. But here are two numbers. One was foul release applied by spraying and foul release applied by brushing. And the brushing had a higher number by rollering. Rollering was a higher number than the spraying. So another factor. Spraying is always better than either brush or roller. Thirdly, the person, the individual who's doing the application has a huge influence. There are PhDs who formulate anti-fouling paints in all the paint companies. But at the end of the day, they give that to a sprayer. And that sprayer can give you a good result or a bad result. It's very, very much surface dependent. Even in this academic work that was being done, the same tin-free SPC paint was applied in 2 locations. One was the ECT, the Emerson Camotation Tunnel in Newcastle, and the other was Sepijar, which is in the El Pardo tank in Madrid. And you can see a huge difference in the finish. The guy in Madrid was a professional applicator, and it was a bigger panel, and he just wet at it, and he got 34, which is very low. So, here's some ship pictures in dry dock to sort of illustrate that. One of the reasons, and the reasons why you might get such variation. When you're in a cherry picker, usually you have 2 people. One is doing the spraying and the other is driving the cherry picker. If those guys don't have good communication, you can end up with a bad paint job. You've got 2 sets of sprayers either side of the bow there. They're going to get overspray. You're going to get a bit of mixture there. And the top right there, there's a painter with what's called a pole gun, spraying with a long arm there. And that is going to be giving you a very different result depending on how close or how far away he is from the ship's surface. So heterogeneity is absolutely par for the course when it comes to painting ships. There's a great deal of variation that goes on there. Final 2 points about the application. The environment makes a huge difference. In particular, the wind, rain, temperature, any of these things can kind of negatively impact painting. And I said to you that 3/4 is the paint preparation, and so 3 out of the 4 things that are involved when paint. When you get to the paint properties, the actual paint itself, which is what the paint chemist can do anything about, he can't do much about the rest. You've got hold up versus sagging, you've got the issues of cold flow. Cold flow is where you put a lot of paint on very quickly when it's cold. It retains the solvent, ship goes to the sea, and you get impact from the waves, and it pushes the paint back. First time I saw this was when the QE2 was painted in Southampton. in November when it was cold, and it took an Atlantic crossing to New York in a storm, and it was getting pounded, and the paint just got smeared back, made it very, very rough. Sagging, this is a particular issue, can be with foul release paint. Silicones, you can paint it and it looks lovely. You turn your back and go away. Come back 10 minutes later and it's dripping down. They've got a definite serious sagging problem unless you formulate it right. Now, SPC paints can help you overcome some of the deficiencies that you have with painting. This is a very old picture from the original SPC1 in 1975. Originally, there were 4 coats of paint, grey, white, on top of this roughness peak, which is an anti-corrosive defect in the paint. And it had 4, almost like a little mountain on the top of that. But after being at sea, that mountain has significantly decreased down to more like a molehill, because in the valley you haven't got the polishing. So that's why SPC paints have a significant advantage, and indeed when they first came out, because ships could get smoother with time. Very unexpected result. So that's why SPC works. Now, in terms of applications, where are we going in the future? Is anything being done about it? Well, those of you who are the avid readers of the IMarEST magazine will have seen this little snippet in the last month's edition about a trial that was carried out actually last year in Bloem and Vos using an automatic robotic paint applicator. And I've got a little video to show you of that being carried out. I'm afraid it was, Jotun may not be here, but it's a Jotun paint that's being applied. And the other thing to say is it's only the sides, the straight areas that could be done with a robot. There are sprayers, you just see them in the video if you're quick, in the sort of curvy areas that you can't get there yet. But anyway, let's have a look at this video. Plus wake you up a little with some nice music. It's only a minute. Where's it gone? Oh, there we are. That's the surface preparation going up and down, up and down, up and down. Spraying on the left. So that gives you some idea of painting in dry docks and everything. The fine print talks about the process has resulted in 30% less coating being required, as well as an exact and uniform color composition. Additionally, it results in a less rust surface and smoother application. So maybe robotic painting will develop. I can imagine that it costs a fair arm and a leg investment by Bloem and Vos to paint this. So, painting depends on the substrate. Substrate preparation is key. The method, the environment, the paint properties are all elements that have significant part. So, let's move on to my second part of my presentation, which is how does surface roughness affect drag? 3 years ago, Mehmet Atlar at Newcastle University said to me, are there any projects that we could work on that would be particularly interesting? Well, when I was, again going back to when I first started in paint, I was given the impression, told that once you get below 50 microns on a ship, you wouldn't get any further benefit in drag reduction. And I've often wondered whether, is that actually true or not? So when Mehmet said, do you want to have a project done? I thought, well, I now work for a company that makes pigments of any size we don't commercialize, but we can make pigments any size you want. So let's have a go at that. So a PhD student started, Chang, and he's been studying the effect of different sizes of copper oxide particles in this case, with a D50, which means 50% is above and 50% is below, the medium size, going from 2 microns, 7, 12, 17, I've put those in yellow because those are the commercially available sizes, and then 25, 60, 100, 150 microns. So going up quite a wide range of paint, pigments, and we incorporated these into I call it a coating. I mean, it's not really a coating, but using the minimum binder possible. What we're interested in was what effect do these particles, these pigments, you've heard about sand grain, it's a bit like that. What effect do these have on the drag? Wanted to combine them together with the minimum amount of binder possible, and spraying them onto a special panels that Newcastle University has using air-assisted airless spray. The binder we used is actually a yacht product from International Paint. Well, it was Extensor, a Swedish company before that, which is it has a copper hat containing component, and then most of the base is solvent with a very little binder. So we mix 3 to 1, 3 parts of the copper oxide to 1 of the binder, and you end up with a almost pure copper system. 94% copper, 6% is the other part that binds it together. These are then sprayed on acrylic panels. This is showing what the panels look like with the taping around the edge, and then put into the flow tunnel. You've already seen Mike's flow channel pressure drop test facility. This is what it looks like in Newcastle here. The test section itself, I'll just show it you there, is there, and you can see these. You undo these bolts, and that's the top panel, and then underneath it is the bottom panel. This is the test section here. Here's the pressure measurement equipment, and then behind it you've got the tank, which keeps the reservoir where the water is. So this is we're looking at it. Now, we looked at a number of different things. The first thing we looked at was the surface profilometry, taking these panels and then doing an area 9 centimeters by 6 at either end, and looking at what the surface is. Surprisingly, the 2 micron panels were actually quite rough. The 7 one as well started to get much smoother, 12, 17, 25, and as it went up, you can start to see, and when you get to 250, you've got a really rough surface. So we've got this whole spectrum here. We'll come to the 2 and 7 in a little bit, because they stand out. In terms of what these look like under the microscope, scanning electron, when the panels were being sprayed, Chang also did small microscope slides that we could then put into the SEM to see what they look like. One is a top view and the other is a side view. Now this is the 2 micron one. What has happened here is these small, very small particles, the scale at the bottom is 20 microns, actually agglomerated. And of course there was a sprayer, and I've told you earlier, the sprayer has a great effect on the end product. So that was the 2 micron one. That's the 7. And again, this wasn't as good as it should have been. Well, I was expecting it to be. I'll just flick through the others here quickly. 12, 17, 25. The scale is changing a little bit at the bottom. So we're now coming out in magnification. 60, 100. That's putting them all together with the magnifications shown at the bottom. The smaller ones were 1500 magnification, and the bigger ones, you're looking at 10 times less magnification with those. What results did we get? Well, this is the raw data for the skin friction coefficients. At the bottom, the yellow line, that was the best one in that series, which was the 12 microns. The 2 and 7, they're up in the middle here. If I can get the point, yeah, they're up in here. Get the color right. The blue here is a 7 micron one. So surprising result in a sense. The actual numbers, average increase in coefficient friction were like this. I've highlighted those 2 at the bottom as being out of step. Another one, if you go up on the right hand side, you can see the range of results. Whoops, pressed the wrong button there. You can see the range of results. And they actually go up in a logical sequence. If you take those 2 out, you're going up and up. This 61 looks a bit odd. there's quite a bit of overlap here between the 17 and 12. However, what I then did was plot them on a graph, and you get this graph here, which is D50 along the bottom, which is the median particle size, and up there you've got the increase, percentage increase, and it shows you, I keep pressing the wrong button, where have I gone? These two, which are anomalous, and this one, the 60, does look a little bit out of place. So Chang then did a second series, because we thought we're going to have to repeat this. Is this a genuine effect, or is it some artifact? This was the respray of the 2-micron one compared to what it had been previously. That's the new, that's the old. And the same with the 7. We did it, repeated that, new and old. And in terms of the numbers we got in the second run, which is on the right-hand side compared to the first, this is, the 2 microns still showed this very, very surprising result. Second time around, the 7 micron actually came right down because the applicator did a much better job, took a lot more care. And the 61 also changed quite a little bit. I've just highlighted there. We then ended up with that graph. So that's starting to look a lot more sensible. Now, so going back to the original question, is there a surface roughness below which no further improvement in drag reduction occurs? The answer is no. The smoother the better. Finally, because we've got biologists here, I have to, and because also Chang, part of his work is going to see whether he can grow stuff on it and then measure the biological influence. What about the anti-fouling properties? He's constructed this box where he slid these panels in. It's almost like creating a little artificial sea chest for these panels, and he put them out in the North Sea in the UK in May, and then examined them last month. To my amazement, it was covered in tube worms. I think of the northeast of England, actually very low fouling area, but if you hit it at the right time of year, covered in tube worms, mainly tube worms, unless sharp-eyed people like John Lewis will be able to tell me all the other species there as well. And if you look inside, here's what was looking at here. Now, there are two things here. One is the edge, what I call the edge effect. This is a copper containing 94% cuprous oxide, so copper is coming out of that quite significantly. To me, it's a bit like having old wooden ships in the 16th, 17th century used to have copper plating on them. It's almost like you've got a copper plate there. Cuprous oxide gives out more copper than copper metal, so it's got a bit of what I call throwing power there. Interesting also, the join here between a non-toxic and this is non-toxic. The join, for some reason, hasn't got tube worms in, so there's something going on actually in that join. There's no anti-fouling in there at all. So, nearly finished. Chang that's the guy doing the work. PhD students these days are quite different. I went to visit him last week, and then he had nearly a three-piece blue suit on. Amazing. Those of you who know Newcastle, that's in the Armstrong building. Obviously, Mehmet, who set up this project to start with, so I've got to thank him very much. Newcastle gave him trouble, so he's now in Strathclyde. Irma Yegenbayeva did a lot of the work on the flow channel, setting it up, and Chang's supervisor now in Newcastle is Mariam. So that's the end of my talk. If you happen to go through Hong Kong on your flights, you might come across this go with the flow drink that Cathay Pacific give you. Encouraging better circulation, beetroot, carrot, apple, mint leaf, and lemon.